So 7.4b will be still within the umbrella of, quote, basic trig equations. The point of this lesson is just to show that we can use some advanced techniques that we learn in algebra in the context of, well, trig equations. Remember back in Algebra 1 or Algebra 2 when we first learned how to solve equations? We first learned about the basic inverse operations. If you see a plus 7, you do a minus 7. If you see a times 3, you could do a divide by 3. But then we start talking about more complicated equations like polynomial equations. Basically, in the world of basic algebra, if our equation is anything complex, we probably need to use advanced methodologies and techniques. And one of the most useful techniques or useful idea in the world of real valued functions is the idea of the zero product property. So recall from, I don't know, Algebra 1, the zero product property. The zero product property states, over the field of real numbers, which is what we'll be working with, if you have a multiplication problem and it equals 0, then either the first factor equals 0 or the second factor equals 0. And this is a very useful thing for us when it comes to solving, because it allows us to break complex or complicated looking equations into smaller manageable pieces, assuming, this is a big assumption, assuming you can factorize the original statement. So that's sort of like the whole theme of today's lesson is, if we are faced with a trig equation that looks complicated, if we can factor it, and that's a big if, we can apply this idea. Remember that in order to use the zero product property, you have to move everything onto one side. It needs to equal 0 first before the zero product property applies. So for example, if I ask you to solve, I don't know, 2 cosine squared theta minus sine cosine theta plus 3 equals 0. Yes, this is a complicated looking equation because I have multiple terms of cosine. I have a cosine squared and a regular cosine. Now you could do what we did in the first half of the unit. Oh, I see a trig function being squared. Use Pythagoras' identities. But Pythagoras' identity would make this more complicated looking than it already is, because Pythagoras' identity will change this in terms of sine squared, and usually equations are easier when they're the same trig type. So although we do have multiple trig terms, notice they're the same type, cosines basically. Recognize that this is actually a quadratic. What do I mean? We have cosine squared, we have cosine, and then we have no cosines. So the idea is, I'll switch colors, so this is like my thought process. This is similar to x squared, I'll use a big X, minus 7x plus 3 equals 0, right? Where the big X is cosine theta. So I hope you guys can recognize that these two equations are basically the same structure. 2 times something squared minus 7 times that something plus 3 equals 0. 2 times cosine squared minus 7 times that cosine plus 3 equals 0. So however you solve this type of equation should be the same way you solve this type of equation. And of course, with quadratics, we should be a little bit more comfortable solving them. We have factoring, and if you really choose to, it's going to be very ugly and messy. We could use the quadratic formula instead. But I believe these practice problems will be designed to be factorable, so we should know that this type of quadratic is factorable. What is that? Is it a minus 3 here and a minus 1 here, right? So if this problem factorizes into 2x minus 1 and x minus 3, then I know, therefore, switching back to black, 2 cosine squared theta minus 7 cosine theta plus 3 equals 0 should be the same as 2 cosine theta minus 1 and then cosine theta minus 3. So see how it's the same technique, except instead of regular x's, we're dealing with cosines now. Now the zero product property can be applied. Since I have factored form equals 0, I know for a fact that the first factor 2 cosine theta minus 1 could equal 0. And then the second factor, cosine theta minus 3, could equal 0. And then we just have two separate problems to solve, and then we'll merge our answers in the end. So for the left equation, hopefully after doing 7.4a, we can pretty much go straight to the answer. Add 1 divided by 2 gives us cosine theta equals 1/2. So I know that the reference angle is what? Pi thirds. And we have cosine theta equals positive 1/2. Cosine is positive in the first and the fourth quadrants. So if I put my reference angle of pi thirds there, one angle will go positive, and then the second angle will go negative. Oops, thirds. I hope it's very clear that these answers are not symmetrical, so we're going to have two statements. All of the yellow answers and all the pink answers. So from this guy here, we have theta equals pi thirds plus, and then to get to my next yellow answer, you have to go full circle. So that's 2 pi. Okay. And then for the pink answer, negative pi thirds plus, and then to go from one pink answer to the next pink answer, you have to go full circle. So that's plus 2 pi k. Now let's talk about the right equation up here. So we have to add 3 to both sides. And now 3 is not a special side length of the 30, 60, 90, 45, 45, 90 triangle. So we'll take the inverse cosine. Now immediately you should see something wrong here. Now let's pretend you don't see it. You know, not everyone remembers everything. You try to punch into your calculator, and it's going to give you a domain error. Remember that in the unit circle, all of the values are capped by 1 or negative 1, and at least in terms of sines and cosines. So we should know that the inverse cosine, whatever you put into here, can't be bigger than 1 or less than negative 1. So immediately I know that this guy right here gives us no solutions. So this, what we said at the beginning, are the only possible solutions to this equation. So it's the same logic, same thought process that we talked about yesterday, except you might have to utilize the technique of factoring. That's about it. That's the only extra layer I'm adding in 7.4b compared to 7.4a. Since I don't want to just leave you with one example, let's just do another random example. I'm going to pick straight from your textbook here. Say, suppose I ask you to solve, I don't know, 5 sine theta cosine theta plus 4 cosine theta equals 0. Now we can see that this is a quote hard question because we have sines and cosines. So in general, the more trig functions you're mixing up, the more complicated the problem gets. And I can't use any identities because it doesn't fit any patterns. I don't see any squares, so I can't use any Pythagorean identities. Well, think more basic than that. We should recognize that, hey, we got two terms here, and they both have a cosine. So in math, when things share something in common, you just factor it out. So we'll go ahead and factor out the cosine here. And we're left with 5 sine theta plus 4 equals 0. So now that it's factored and it equals 0, we can use the zero product property. The first guy says that the cosine of theta could equal 0, or 5 sine theta plus 4 could equal 0. So let's go ahead and solve the right-hand side, right equation pretty quickly here. We're going to subtract 4 and divide up the 5. So we get sine theta equals negative 4/5. Now this equation is pretty interesting. Cosine theta equals 0. Now 0 is certainly not one of the special side lengths of the special triangles. But we have to remember that we are working on the unit circle, and cosine stands for the x-coordinates of all terminal points on the unit circle. So what angle can you think of on the unit circle has an x value of 0? Well, hopefully you guys can just see, or can wrap your minds around, that at 90 degrees, or pi halves radians, this coordinate here is 0, 1, and at 270 degrees, or 3 pi halves radians, this has coordinates 0, negative 1. So for this answer at least, we have pi halves and 3 pi halves. Now, notice how they are symmetrical with each other, so we may not need two separate statements. But I want to check this answer first, though, because sometimes all of them could be symmetrical with each other. So here we have to take the inverse sign. Okay. Now, off the top of my head, I know 4 and 5 are not special side lengths, so unfortunately, we're going to have to use a calculator. So taking the inverse sine of -4/5, or actually just, I like to ignore the negative, so it's your choice. If you want to utilize the negative, go ahead and use it. I like to ignore the negatives and just treat that as a reference angle. So I'm going to take the sine inverse of a +4/5, and I'm going to get about, so squiggles, 0.93 radians. So let's go ahead and blend or put all the answers together here. So I know that sine is negative in the fourth and the third quadrant. So this is 0.93, 0.93. So that means this answer here, theta 1, is going to be 0.93 plus pi radians. And let's go ahead and get a decimal approximation. If we're going to use a decimal approximation, might as well approximate pi as well. So that's about, let me get a calculator, that's about 4.07 radians. And then this guy here, theta sub 2, I'm just going to use the negative angle. I think that's easier. Theta sub 2 is negative 0.93. So if we were to blend this picture and this picture together, here are our solutions. We have one solution up here, so I'm going to try to bold this. We have one solution down here. We have one solution right here, so that's 0.93. And we have a solution right there, 0.93. So I know already that these guys are symmetric, but I'm just going to go ahead and highlight each answer separately. So we got one answer at 90 degrees, or pi halves radians. Pi halves. 3 pi halves. I got another answer at 3 pi halves, another answer at what we say 4.07, another answer at negative 0.93. Now, sometimes, you know, since this is a sketch, you really can't base it off of appearance alone. But I hope I don't have to do any math to prove it to anyone that these 4 answers are not symmetric with each other. There's no way that these angles here, which is bigger than 90 degrees, is equal to this angle here, which is equal to this angle here, which is equal to this angle here. So all of them are not symmetrical with each other, so we cannot merge this as one statement. But I hope everyone can agree that at the very least, the pi halves and the 3 pi halves are symmetrical with each other. So those I can merge as one statement, and then this answer can be its own separate statement, and then this answer can be its own separate statement. So I should have 3 final statements in the end. So let's go ahead and answer this question. Theta can equals, let's do the yellow. I can start anywhere I want. I can go to this angle, or I can go to this angle, or I can go to this angle. It doesn't really matter. I think pi halves is a natural choice. So pi halves plus, so starting here, how far would I have to travel before I hit the next yellow answer? Only 1 pi. So I'm going to add plus pi k. Let's go to the blue answer. So this right here we've already said was, what was it, 4.07. So how far would I have to go? There we go. How far would I have to go if I'm already right here? So I'm already right here. How far would I have to go before I get to the next blue answer? Well, I'm forced to go a full circle. So this will just be plus 2 pi k. And then let's go to the red answer. So you can go all the way to get the positive angle, or I'm going to be lazy. I'm just going to take the negative angle here. So negative 0.93 radians plus. So if I start at the red angle, how far would I have to travel before I hit another red answer? I have to travel a full circle, or 2 pi k. So that right there, where all of the k's are any integers that you can think of, that right there would be the general solution. So there you have it. You know, so nothing has really changed conceptually in terms of writing down your answers. It's just you might have to use quote advanced algebra techniques. Namely, sometimes you might have to factor. Good luck.